Let's consider the least squares criteria where we only have horizontal lines. So in other words, our y vector is just like before, y1 to yn, and our regression vector is simply a vector of ones, and I label that jn. So we want to minimize the Euclidean distance, the squared Euclidean distance between y and jn times mu, or a constant vector. This will basically find the best value of mu that minimizes the sum of the squared distances between the observed data points and that value of mu. We can solve for this very easily. For mu as a real number, we can expand the square and get y transpose y minus 2jn y transpose mu plus jn transpose jn times mu squared. We can simplify this as y transpose y minus 2ny bar, because jn transpose times y is just the sum of the elements of y, which is ny bar, times mu, plus jn transpose times jn is n, so plus n mu squared. If we take a derivative with respect to mu, we get negative 2ny bar plus 2n mu. If we solve that equal to 0, we get that mu hat is y bar. We can check a second derivative condition easily by just taking the second derivative, for which we get 2n, which is strictly greater than 0 over all possible values of mu. So we know that we have mu achieves a minimum for this particular criteria. So that's probably the easiest version of least squares, where all we want to do is find the best constant value that represents our data. So if we had to pick a prediction and we had no information, no regression variables, our best prediction, at least as far as least squares is concerned, would be the sample mean. So after this, we're going to consider some more complicated settings.